Partial dependence can invent feature combinations your data never contains. PyALE measures local prediction changes within observed ranges, so correlated tabular features tell a more believable story. You'll learn the shape of a workflow that plots feature effects with uncertainty while staying inside observed feature pairings. I'm Professor Pi, teaching AI foundations with simple Python. When you train a model on tabular data, correlations are normal. Size goes with rooms in housing, age with income in surveys, engine size with horsepower in cars. Partial dependence plots and their grids pretend you can vary one feature while everything else stays fixed. And that often forces the model to speak about impossible combinations. ALE, accumulated local effects, avoids that by nudging a feature inside local neighborhoods where the data actually lives. The payoff is explanations that reflect observed pairings. The trade-off is that very sparse neighborhoods can still be noisy, which is why we add interval estimates. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Now, we build the toy dataset, train a model, and print the correlation so the problem is visible. This snippet builds a tiny correlated housing dataset and trains a scikit-learn RandomForestRegressor so we can see the correlation in action via feature core. Rooms is repeated in small groups. Size is generated from rooms plus light noise. And X keeps both predictors in a pandas data frame, while Y combines their contributions into a simple target. The printed feature core makes the relationship obvious, and that sets up why a grid-based partial dependence would mix unrealistic pairs. Next, we test how many hypothetical grid points fall outside the real conditional ranges, so we can see the failure mode. This example counts how many Cartesian grid points fall outside the observed conditional ranges to make the partial dependence failure concrete. A PD-styled grid naively crosses every room's value with every typical size value. Our min-max records the observed size range within each room's group. Pairs builds that full grid, and inside checks whether each row respects the relationship in X. The printed PDP impossible pairs shows how many of those grid pairings never occur in the real data. Having shown impossible pairs, we run one-dimensional ALE for both features to see which has the larger local effect across observed neighborhoods. This snippet uses PyALE to compare one-dimensional accumulated effects for rooms and size, and then ranks them by spread in the F column. The loop calls ALE for each feature with plot equals false, so we inspect the returned data frame directly. Effects stores the span of F for each feature, letting the code identify top feature as the one whose ALE curve moves most across the data. That tells us which feature has the more pronounced local effect inside observed pairings. Now we focus on the size feature and add interval estimates so we can judge stability across bins. This code adds confidence intervals to the PyALE result for size, so we can see how stable local estimates are across bins. Feature type equals continuous makes the intent explicit. Grid size equals 4 keeps the output compact for teaching, and include CI equals true with C equals 0.95 asks PyALE to attach interval columns. Larger grid size gives finer detail but fewer points per bin, so intervals can widen. The printed CI columns and CI rows confirm that the ALE table now carries interval information. Finally, we produce a matplotlib figure that combines the ALE curve and its uncertainty into one visual you can use to explain model behavior. This example finishes with a small PyALE and matplotlib baseline plot that draws the ALE curve and its confidence intervals into one figure for easy interpretation. plt.subplots creates fig and ax. Then ALE is given those objects, so PyALE draws directly into the provided axis. Grid size 6 smooths the curve a bit compared to the earlier table, while keeping binning interpretable. The printed plot axes and ALE points verify that one plot was created and that the ALE table contains the curve points. You can map this toy example into a real project by replacing the tiny dataset with scikit-learn California housing, or your internal housing table, training the same random forest regressor, and plotting ALE curves for the features that are strongly correlated in your data. A quick summary: ALE, for correlated features, measures prediction changes inside observed conditional ranges, so explanations stay realistic. Use ALE when features are correlated, and partial dependence would average over impossible combinations. And watch out for very small bins or sparse regions. Those give noisy local estimates, so read the intervals cautiously. A clear next step is to run this same pipeline on the scikit-learn California housing dataset and increase the ALE grid density while watching how the confidence intervals respond. That will show if finer bins give more detail or just more noise in your real data. If AI foundations in Python help, subscribe and watch the AI Foundations videos.